All righty. Sorry for the delay, everybody. For some reason, even though I'm teaching in this room, they still do not trust me with the keys to this room. So thank God for the guys over at the other building. But before we begin, I haven't graded your exams yet. I just turned them into the scanning office this morning. So hopefully by the end of the week, I'll have those grades done and posted. If any of you were not able to take the exam on Friday due to quarantining or an excused absence, be sure to email me and schedule a new time to take that exam. Otherwise, that's a zero. So make sure you email me and be proactive about that because this is a very short class. There's only a very limited time to get your exams and stuff in. So stay on top of that. As always, keep an eye on Canvas. Still have assignments coming in and those due dates are clearly labeled. So keep those in mind and keep trucking along with those. I think that's it. Any questions on general stuff like that? No? All right. Well, this week we're talking about volcanoes, and it is as if the universe has given us a gift with a massive, massive oceanic eruption over the weekend. So who can tell me where we had an eruption this weekend? Does anyone know? It was in the Pacific. So what else is in the Pacific that we know of? What's that big boundary of the Pacific Ocean? What's that called? Pacific Ring of Fire. And it's called that because it's just a bunch of subduction zones. We've talked about this in plate tectonics. Subduction is where we have plates colliding and one is underriding the other one. It's being melted as it's pulled into the plate. And that creates a lot of instability and volcanism, and all that magma comes up to the surface, and sometimes it erupts, sometimes very violently. So this is taken from one of the satellites orbiting Earth. Yeah, this is a huge, huge eruption. You can see it from space. There's a huge risk of tsunami. There's a huge risk of potential aftershocks from earthquakes. So this is a huge event. And just to put that into perspective, that's that same eruption over the country of France to the left. So this is a huge, huge eruption, and this is what it looks like on the ground. What you get a lot of whenever you have violent volcanic eruptions, all the ash that's brought up into the sky doesn't create electrical storms, but it creates static electricity. Just that violent surge of new material being forced upward into the stratosphere just causes a lot of static. So you get a lot of lightning strikes whenever you have violent earthquakes. So you'll see a lot of pictures with earthquakes and lightning coming out of them as well. Journalists love that stuff, so they always make sure to put those into their newspapers and stuff. This is Krakatoa. Krakatoa erupted last year, which was at the time, it was one of the largest eruptions in the South Pacific, but this one beat it by miles and miles. So as it's erupting, it's sending all that ash up, and you can see all that static electricity arcing throughout the ash column. So it's pretty cool. But the reason this specific volcano erupted, this volcano has been erupting for hundreds of thousands of years. It finally breached, it was an undersea volcano, an underwater volcano, because remember, we're in the Pacific, where oceanic plates are very, very low below the surface of the ocean. So this took a long time to breach the surface of the water. It just breached the surface of the water in 2009. So it was a relatively new island. So this was essentially two islands. You have Hunga Tonga and Hunga Ha'apai, which are two parts of the same volcano. So you have these two breaches of these islands as part of the bigger central volcano. So the center of the volcano was underneath the water, about 150 meters underneath the water, a football field and a half. So whenever this erupted, number one, anything living on the island, which because it's relatively new, nothing was really living there except there was this one colony of owls that that was of great interest to a lot of biologists, and now it's completely gone, which is sad. But basically, we had this huge eruption that displaced 150 meters of water. So remember when we were talking about tsunamis and the deeper portions of the water and the deeper column of water that you have for a displacement, the greater the tsunami risk and the bigger wave action that you have. Because it's only 150 meters, we didn't have a big tsunami risk from this. We were concerned about it just because of all the potential aftershocks and other earthquakes that could happen from a violent reaction like this. But luckily, the two islands poised on either side of the eruption really helped dampen that wave velocity. So by the time it reached, like, say, South America, we only had like maybe 2 feet in difference. So something you wouldn't even notice with the normal tides coming in and out. There were 2 deaths in Peru that they think were attributed to, they say, anomalous waves. So most likely there were 2 surfers that were out too far, and then as the waves came in and back out, they just got drug out to sea. So sometimes that happens, but luckily not huge tsunamis. A lot of coastal flooding, but not huge tsunamis. But it was pretty cool that that happened this weekend, and we can talk about it in class. So we study volcanoes a lot, mainly because volcanoes are all over the surface of the earth. People have lived near volcanoes for a number of years and for many different reasons. One of the main reasons, it provides really, really fertile soil. So there are people that live in these, this is an extinct, extinct volcano in Ecuador. Ecuador is part of the Andes Mountains. So these are highly volcanic mountains. Some of them are now extinct or dormant. So they're not very eruptive. But because they release all these fresh new minerals from the center of the earth, it's a perfect place to cultivate crops and grow different strains of horticulture and agriculture. So it's really important for people that live in these rural areas near volcanoes because they get access to that really great soil. So pretty much everything that you enjoy, from fruit to coffee to beautiful flowers, they grow in mostly volcanic soils. Specifically, like in Italy, I mentioned San Marzano tomatoes grown right on the slopes of a volcano. That's why they're so expensive, but that's also why they're so good. They draw all that mineral content up into their root system. Fast forward to the 21st century, now we care about geothermal energy. So not only can it provide food for the human race, it can also provide energy sources. So geothermal energy is just the process of drilling pipes and laying pipes near volcanic sources, real large heat sinks on the earth, running water through those, getting that water up to boiling. That boiling water powers a steam turbine. Boom, you have electricity. Really simple process, but very expensive, very costly to maintain, but it is a very, very good renewable source of energy. There's practically zero waste produced from this because any emissions that you would get from this are caused by whatever volcanic or magmatic source that you're using. So you have net zero emissions. So a lot of countries are using geothermal energy, us included, but only in limited places. Obviously, it has to be near somewhere that's close to the earth. Remember, we have to dig very, very deep in most of the areas of the crust to get to even remotely hot areas inside the earth. So you want to be near volcanic sources, like in Iceland, where they're basically made of volcanoes, essentially. We also care about the ore deposits and materials that come from volcanic sources. So this is pumice. Some of you may have seen pumice before, very light, very abrasive, so it's really good at scrubbing stuff. Cultures way long ago in the past used these for washing things just because of how abrasive it was. And people use it today for skincare, obviously, so they're very good for abrasives. And obviously people like living near volcanoes because they're very scenic. That's Mount Rainier out in Washington. Beautiful place to live, very expensive skyline, very expensive apartment prices. I've looked into it. Same with Fuji, Japan. Fuji is considered the most beautiful mountain in the world because it is just almost perfectly symmetrical every way you look at it. It looks exactly like that, 360 degrees around. It's pretty incredible. But then you can also get the scenery that comes from existing volcanoes. This is in Hawaii. They have their Volcanoes National Park. If any of you have ever been there, it's a really cool place. You got probably the youngest rocks in the world right underneath your feet. Some of them even younger than you. That's how new and fresh rocks they are. But because they're constantly erupting and bringing lava up to the surface, they're basically killing any vegetation in their path. So it's also a huge hazard. So why have we lived near volcanoes? Not just for agricultural reasons, not just because a lot of them occur near the coastline, but also because of religion and mythology. So in Hawaii, they have the god Pele, who was this volcanic goddess. If you're familiar with most of the Pacific Islander theology, that's a big portion of it is volcanic deities, as well as with the Greeks and the Romans, Hephaestus. They believed that volcanoes were basically the forges of the Greek god Hephaestus, who was a craftsman. So they've played a really important role in human civilization since the beginning. So now we're getting into what we care about, is the hazard of volcanoes and why they occur, where they occur, and how we can better forecast and prevent disasters. So this is from Mount St. Helens, roughly in 1980. One of the most explosive ones in the 20th century. Basically half the entire mountainside just collapsed and blew out like a shotgun blast. Very, very devastating eruption. And sometimes it's not just the actual blast of the eruption, it's the ash fall that you get from the eruption. So if you can imagine a huge column of ash, eventually what goes up must come down. We have laws of gravity on Earth. So if you have massive amounts of ash flowing into the stratosphere, they're going to spread out and they're going to fall like snow. So back in 2010, Eyjafjallajökull, which was a huge volcano in Iceland, it erupted for, I think, 5 days, I think, 6 days. Yeah, erupted for 6 days. It grounded pretty much all air traffic in Europe. You could not fly in or out of Europe for probably a week afterwards, just because there was so much ash, the visibility was so low that it would have been unsafe for pilots to fly. And then you get these huge deposits of ash that just fall like dust everywhere. You got to wear a mask everywhere, as you're probably used to by now, but back in 2010, we didn't have to worry about that. So yeah, it causes a lot of problems. So it causes so many problems that a lot of times you have to evacuate. So this is in Bali. So 100,000 people were displaced during this eruption just because of how much ash was brought up. So the air quality was extremely low. So everyone had to evacuate the area. And we've been studying volcanoes since recorded history itself. Most of you are familiar with Pompeii and Mount Vesuvius. The people of Pompeii lived near Mount Vesuvius for the same reasons that most people live near volcanoes now. The fertile soil, it's picturesque, it's right on the coastline. It was a great place seemingly to build a city in the Roman Empire. But As we know, most of it was buried under what's known as pyroclastic flows. Pyroclastic flows are just, imagine a landslide or an avalanche made up of molten rock, ash, lava flows, just the worst thing to be in front of, basically. That's what a pyroclastic flow is. And these can travel incredibly high speeds over incredibly long distances because there's so much energy behind them. So that's why the entire city of Pompeii was just covered in ash and volcanic rock. And that's why it was also so well preserved. That's why you can go visit it today, because it was just so quickly buried. Okay, so we've done this so many times. You guys should be experts by now. We're going to do a recurrence interval of Mount Vesuvius. So for 700 years, it was inactive. It erupted in 79 CE, so after the year 0. And then it erupted how many more times? 79, 203, 472, 512, 685, 993, 1036, 1049, 1138. So that's 9 eruptions from 79 CE to today, or excuse me, to 1138. That'll be your last one. So 9 eruptions over that period of time. What's the recurrence interval? Yes. B, 132. Very good. It is B. Well done. So just like with earthquakes, we're going to calculate recurrence intervals for volcanoes, because that helps us establish whether a volcano is dormant, whether it's extinct, or whether it's active and potentially hazardous. So remember that whenever we calculate recurrence intervals, we are forecasting. It is just the probability of an event happening in a certain time span. It's not saying this volcano will erupt on this day, in this year, and at this time. That's prediction. We can't predict things, but we can forecast. So, for example, if our recurrence interval was 132 years, for 500 years, nothing happened at all. And that doesn't make sense. But an eruption happened in 1631, killed 4,000 people. Still pretty devastating. A recurrence interval is just a probability. It's a statistic. That's all we can do. But the more data we have, the better that we can be with monitoring and warning systems. So what is a volcano? Basically, it's a hole in the Earth's crust where fresh magma can come to the surface. Once magma is on the surface, it's called lava, as I'm sure you guys know. But basically, it's a space where ash, lava, and gases from beneath the surface can flow up to the top of the surface. Got to get that out of there. So most of the Earth's volcanic activity is associated with divergent boundaries, but most of the world's most explosive volcanoes are in the Ring of Fire. So why are they in the Ring of Fire? Who can tell me? Yeah. Subduction zones. Very good. Like we said before, with talking about Hunga Tonga over right in that lower left corner, right to the north of New Zealand. That's where that volcano erupted. That's the Tonga Trench. Remember, whenever we have subduction zones, we get trenches because you get that very deep part, that wedge where those plates are kind of pulled. So the Tonga Trench is a subduction zone. You have trenches along Peru and Chile, where we have the Andes Mountains, also volcanic. You get a lot of volcanoes in Central America, also a trench there, that's a subduction zone. All of the Aleutian Islands in Alaska, those are subduction zones. They're all volcanic. And the same thing as you go from Kamchatka all the way down through Japan and Indonesia. So subduction zones not only produce the most powerful earthquakes on Earth, but also the most powerful and eruptive volcanoes on Earth. So as with everything, not all volcanoes are the same. They have a lot of different characteristics, and they're based on a number of different parameters. One of them is the type of lava. So if we have Hawaii, for example, Hawaii doesn't have these huge peaks of volcanoes. They have these very large, like rifts and fissures where the volcanic material and lava just leaks out, kind of, and flows like a river. But in Stromboli, Italy, we have these huge peaked mountains, those like real typical what you would draw if you were to draw a volcano. That triangular shaped mountain, ash spewing out of the top of it. Sometimes we get calderas or craters, like in El Salvador. That's where we have these huge volcanic towers that just collapse in on themselves. So most of this is due to the type of lava. It's also due to the type of pyroclastics. Pyroclastics is just the stuff that comes out with the lava. So you have your ash, your gases, your vapors, different formed rocks, like actual whole rocks. Those are called lava bombs. Basically, these just molten rocks that aren't completely melted yet, so we can't call it a lava. Also, its explosive potential, its shape, obviously the recurrence interval, otherwise known as the eruption frequency, the degree of the hazard, and all of it is determined by the volcano's magma chamber. All the magma chamber is where all that material is stored within the volcano. So we've talked about igneous rocks before. Igneous rocks form from crystallizing or freezing of magma and lava. All of that molten material gets brought up to a point where the temperature is low enough that it can recrystallize and harden into an actual rock. So magma is from the partial or complete melting of those rock materials that are inside the earth. Whenever you break down a subducting plate, you're melting it down into magma. So as we've said before, and as I'm sure in your grade school class, magma is under the surface, lava is above the surface. So magma chambers are, as you can imagine, the storage vaults of magma underneath the surface of the earth. So most of them are roughly 4 kilometers to 50 kilometers. So in terms of the surface of the earth, that's pretty shallow. You have to have the right conditions, temperature, pressure, and the containment structures. Whenever we're talking about containment structures, we're talking about the geology around the magma chamber. If we have like a lot of well-defined rock formations that aren't partial to melting, if we have enough void spaces, if there are faults or fractures that lava can preferentially flow and break those rock formations down, that's what we're talking about with containment structures. So based on these characteristics of the magma, we can determine what style of eruption we're going to get. So we get a lot of different types of eruptions, ranging from very gentle to explosive, like we saw a couple days ago. So most of these are determined by chemical composition. That's the big one. The volatiles, meaning the gas content, the water vapor, what other stuff is in it, and viscosity, its resistance or ability to flow. So before we do all of that, we have to melt down the rock. So we have all the rock in the mantle. It's solid, but it's still pretty hot. So how do we get there? You can either get there through temperature or we can get there through pressure. So this is a phase diagram. Geologists use these a lot. This is basically taking a bunch of data that we've collected on the melting points and the pressure points of certain rocks, graphed it all up, and we can say, oh, at this temperature and at this pressure, we have a solid or a liquid or somewhere in between. So the way we read this is that x-axis on the top is temperature. It's increasing this way to the right. Pressure is increasing as we go down on the y-axis. So as you can imagine, with surface conditions up in that left corner, we're going to have pretty much nothing. You're just going to have a rock, right? A rock on the surface is pretty much air temperature in its temperature, and pressure, it's only experiencing barometric pressure. That's all it's experiencing. If I put a rock on this table, it would show up on that top left corner. Low temperature, low pressure. Let's say I start to drill into the surface of the earth. And we're going to go deeper and deeper and deeper. We're going to start increasing the pressure because those rocks are experiencing the weight of everything on top of it, including air pressure. Same thing with temperature. As we get closer and closer to the Earth's core, we're going to increase our temperature as well. So for solids, lower temperatures, higher pressures. Whenever you have higher pressures, as we've talked about, going from igneous to metamorphic, sedimentary to metamorphic rocks, what changes that? Temperature, pressure, and time. So if you get a lot of pressure and you don't need that much temperature, you can change a rock. Have you guys heard of lab-grown diamonds? You've heard of that trend? It's pretty much the same thing. Diamonds are formed through immense pressure. You start with coal, you just put a bunch of weight on it for thousands of years, and then it turns into a diamond. They have the same chemical composition, different crystal structure, just because they've gone under different pressures. The temperature, though, as you can imagine, we can't replicate that kind of temperature of the center of the Earth in a lab. It's just too hot. So just by using temperature, we can turn coal into diamonds. So low temperatures, high pressures, you're going to get solids. Liquids, you're getting higher temperatures, lower pressures. So a liquid, as we know, takes the shape of whatever vessel it is in. There's no pressure on it. The atoms are kind of spread loosey-goosey. They're able to flow. But the more heat we up the heat, we're going to get some type of melt and some type of magma or lava. All right, so this is just to make sure that you guys can read. What phase exists at this star? Just shout it out. Solid, very good. It makes sense because it's in the field of solid, has a relatively low temperature. Remember, we're increasing temperature this way. We have relatively high pressure. So obviously it's a solid. So let's say we take that same rock and we melt it. So if we're moving from there to the field of liquid. So what happened to this rock in order for it to go from a solid to a liquid based on this phase diagram? Those of you in Zoom can type your answers into the chat. Yeah. Temperature increased, right? Pressure stayed the same because it's right in line, but temperature has increased since we're going to the right along the x-axis. So we're going from roughly maybe 950 degrees C to around 1500 degrees C, but we're staying at like 10 to 11 kilobars in pressure. So we can have melt from just changing the temperature. We can also have solidification by just changing the pressure. So this is a pretty key component whenever it comes to melting. Melting occurs whenever you increase temperature and whenever you decrease pressure. If you relieve the stresses of a rock, you're gonna decrease any forces that would solidify that rock. So if we did the same thing, instead of changing the temperature, we just changed the pressure that the rock was experiencing, we're also gonna melt it again. So rocks are especially rocks and magma chambers, they're really complex. They're not, we can't just say, oh, it's all liquid, it's all solid. It's going to be a mixture of everything, because rocks solidify, different minerals solidify at different temperatures. So you can only have one temperature in that given area. You're going to have a different range of solids and liquids. So if we have magma at A at 1200 degrees C, and we start to cool it from 1200 to 600, we're going to change that composition as we go. So this is what has defined igneous rocks, and it also defines how volcanoes form and the types of volcanoes that we're going to get based on the temperature and the chemical composition. As that cools down or heats up, we're going to change that composition from the physical standpoint, liquid or solid, and the chemical standpoint, what kind of minerals that we're getting. So most of our magmas are going to reflect the type of elements that we have in the earth. Obviously, we have an abundant source of elements on the earth, but really we have these main 8 that we can find time and time again in all these magmas and all these rocks. But the number 2, the number 1 8 elements of the 8 elements that we get the most is silicon and oxygen. You see it time and time again in all igneous rocks and in all volcanic sources. All the time, silicon and oxygen, which makes sense because they're the most abundant in the Earth's crust. It makes sense that most rocks would be made of it. If it was made of something like potassium, if all magma was potassium, that would be something very interesting to study. But because it's the most abundant stuff in the Earth's crust, it's a no-brainer, basically. So silicon and oxygen are the dominant group, which makes up the mineral group known as the silicates. So you have everything from quartz, which is SiO2. You get muscovite and biotite, which are micas, which are these like real thin sheet-like rocks, minerals. Muscovite actually used to be used as a substitute for glass back in the Middle Ages, because they couldn't fire glass. It was so thin and you can see through it. You could use it to make window panes. Plagioclase, Si3, gypsum. We have a lot of oxygen in gypsum. Let's see, kaolinite, that's a clay mineral. We get a lot of those in Delaware, a lot of kaolinite. There's a couple of roads called Kaolinite Road, just because of the amount of kaolinite clay that's there. That's Si4. Let's see. Hornblende. Hornblende is one of the main minerals in granite, and we get a lot of granite whenever we're building mountains. So it makes sense that we have a lot of silicon in that as well. So the amount of silicon defines not only the mineral, but the type of rock, and in turn, the type of magma. Okay. So the way that silicon bonds with specifically oxygen is silicon can bond with 4 other oxygen molecules, which forms this structure, which is called the silicon tetrahedra. So you have silicon at the center, 4 oxygens at different points, and it makes this pyramidal triangular structure. And this certain structure ends up being really, really important for how different minerals and magmas form. Because whenever you get one of these tetrahedra, they're going to end up sharing electrons and bonding with other tetrahedra. So you have the single tetrahedra to the left. Those can form in chains by just stacking and sharing those oxygen molecules. You can form double chains by sharing even more. And then if you can make those double chains, you can create sheets of tetrahedrons. And then if you go from there, you can make 3-dimensional networks of these different molecules. So these structures tend to form and break down based on increases and decreases in temperature, as well as the concentration of the silicon and oxygen. So if you get more silicon and oxygen, you're going to most likely get these three-dimensional networks. If you decrease the amount, you're going to get single chains, double chains, maybe. But this is going to define a lot of the other parameters that we're going to talk about, such as viscosity. So as you can imagine, if you have certain presences of these polymers, you're going to get different viscosities. So viscosity is just the resistance of a fluid substance to flow, meaning that if I was to pour something out, how readily is it willing to pour out? So high viscosity, think of like really thick substances like honey, peanut butter. If I, or a DQ Blizzard, no, they turn it upside down. It's not going to flow. They're very thick. They don't want to flow. They're just, yeah, they're just thick, sticky, and stuff like that. Whereas you have something like water or like hot syrup, it's a lot thinner. It's more preferential to run. So if I turned this water bottle upside down, it's going to pour out readily onto the carpet. However, if I turned over a pot of honey, it may take forever for that to completely empty. So high viscosity, greater resistance, low viscosity, lower resistance. So viscosity is largely determined by temperature. So if you have higher temperatures, think of flat hot maple syrup. If we have room temperature maple syrup versus hot maple syrup, that hot maple syrup is going to have a lower viscosity. It's going to flow more readily out of the bottle. So higher temperature means higher energy, lower viscosity. If we have lower temperature, lower energy, higher viscosity. So think of the amount of energy in it is the more energy you have, the more willing you are to flow or run. Lower energy, you're more likely to just stay put, basically. So composition is going to play a good role in it as well. So if we have a greater concentration of silicates, remember we get those chains and those sheets, we're going to get a higher viscosity. It's probably a lot easier to move one silicate tetrahedra than a whole sheet of silicate tetrahedra. Those bonds really strengthen it and prevent it from running. So this is where we're breaking down into, remember, our felsic and mafic rocks. Remember, for our igneous rocks, we have ultramafic and mafic on one side, meaning the basalts. These are our lower viscosity ones. So that's why Hawaii has a lot of mafic rocks. That's why all of the ocean floor at those mid-Atlantic, at those mid-ocean ridges, those are all basalts, which are mafic rocks. And then felsic rocks, we have higher viscosity. We're going to build up a lot more. We're not going to flow out. We're going to be a lot more viscous and not want to flow anywhere. So that's where we get those buildups of those mountains, those volcanic arcs. The Cascades, the Andes, those are felsic rocks. Higher viscosity. So why mafic and felsic? Mainly based on Norman Bowen, who is the founder of modern petrology. Petrology is just the study of the formation of actual rocks. Geology is the study of the hard materials on the Earth's surface, which is the greater overarching science. Petrology is just narrowing it down to rocks themselves, how they form, how they break down, and chemical composition within it. So he took a bunch of powdered rock materials. Basically, you just put it in a rock crusher, and basically it's just a big hammer. So geology is a pretty simple science in terms of materials. Just take a hammer to it and see what happens. So he heated them up, he cooled them down, and then he timed those rates that those minerals crystallized. How long did it take based on their chemical composition, based on where they came from, how long did it take for them to cool and crystallize? So this is where we get the difference between mafic and felsic rocks. Mafic rocks, because it takes them, because they're low in their silicates, they get heavier in density. They get a little more, they have more energy behind them just because they're not linked together with all those silicates. They're just very spread out. So this is where we get our mafic rocks, rich in magnesium and ferrous iron, MaFi. That's where we get mafic from, magnesium and ferrous iron. Not a lot of silicon. However, whenever we get to felsic rocks, felsic, Fel is for feldspar, Si is going to be for silicon. Got a lot more silicate structures in those. So basically, Bowen created this graph, which is the foundation of all petrology, and it's really important in understanding not only where minerals are going to form, what type of minerals are going to form, but also their specific uses. So there's a reason that quartz is so common and quartz is so widely used. It's because it has a very low melting point. It's very easy to melt down in industrial furnaces, so you can use it to make glass. So anything that you have that's made of glass is sourced from quartz itself. But basically, to understand this graph, we're going to start from the top and work our way to the bottom. So we have our ultramafic rocks on the top. Remember, they're going to have lower amounts of silicates. They're going to have the highest melting points. And we're going to move down to mafic and intermediate, and then we're going to get to felsic. Felsic is where we're going to get our continental rocks. We're going to up that concentration of silicates, higher viscosities, and lower temperatures. So remember, low temperature, low energy, high viscosity. Ultramafic, high temperature, high energy, low viscosity. So it's that inverse relationship that we have between them. So basically what this is saying is that if we start here at the highest temps, and we're in a magma chamber, and we have this magma of something. As we cool it down, let's say we're at 1500 and we get to 1200 degrees. This is where we're going to start to get ultramafic rocks crystallizing. This is where olivine is. So 1200 degrees, we're going to get olivine, that mineral olivine, nice green color. This is where most of the mantle rocks are. Olivine makes up most of the mantle. So we're going to continue to cool. We're going to continue to cool, and then we're going to get to our regular mafic rocks. We're going to get our pyroxene, our amphiboles, our basalts, our gabbros. So the stuff that forms at mid-ocean ridges, continental, oceanic basins, real dense stuff, but still high energy. So we're going to get some lower viscosities. So yeah, mafic rocks crystallize at higher temperatures, high density because of that low silica content. Think of stuff that's made of silicon. It's very lightweight. It's very lightweight material. It's very popular in your cell phone just because you're going to carry it around in your pocket. Stuff that goes into your cell phone has to be lightweight. You can't carry around a brick. So silica is very light. So if you up that concentration of silica, you're going to have a much lighter rock. So if you have a lighter rock, you're going to bring it preferentially to the surface. That's why continental crust is made of silicon-rich stuff, whereas oceanic crust is made of more dense materials because they don't have the silica content. They have more metals, iron, magnesium. That's going to sink it down, bring it down into the earth. So because these are crystallizing at high temps, they can crystallize in different places. Remember the difference between intrusive and extrusive. Intrusive means it's forming underneath the surface. That's where we get those granite domes, those basalt domes. Extrusive means it's actually being erupted out of the volcano, and then it's cooling down on the Earth's surface. Okay, now let's get into our medium temp stuff. The intermediate range. As with every scale, there is always an intermediate, something that is in between the two major degrees. So in our intermediate, we're around 800 to 1,000 degrees in Celsius. Still pretty hot relative to us, but for a rock, that's nothing. So this is where we're going to get our biotite mica, our muscovite mica. Oh, sorry, muscovite's at the bottom there. But we're going to get more of our feldspar in there as well. So remember, biotite mica is that sheet-like rock where you can like pull it apart. So remember, we're getting sheets from those silicate sheets from the silicate tetrahedra. So as we're increasing our silica content, as we're decreasing temperature, we're going to change the shape of the minerals that form. So this is where we're getting our more silicate sheets, and it's forming in sheets. So we're going to get a higher viscosity and lower energy. So intermediate, another word for it is andesitic. The reason we call it andesitic is because most of the rocks of the Andes are formed in this fashion. Excuse me. So you get a lot of plagioclase. Some quartz is going to get in there because we get a little bit more silicate content, SiO2. That's the symbol for quartz. We're going to get less magnesium, less iron, just because there's so much silicon in there, there's not enough room for anything else. So we're increasing our silicate content, decreasing our heavy metals, stuff that's going to bring it down. And we're going to get a medium density, still pretty heavy. They can still form continents, but not a lot. So we're going to get these colors of more gray, more beige, real boring hallway type paint colors. So andesite is an extrusive rock. Andesite is formed from a lot of the ash flows and pyroclastic flows that come out of volcanoes. Diorite, same content, but formed intrusively, formed inside underneath the surface of the earth. And now we're finally getting to felsic, lowest temperatures, highest silicate content, lightest rocks that we have. Think about quartz or glass. It's very light whenever it's fired. Even in massive boulders, you can still move it with your hands. It's that light. And we get a lot of our potassium feldspar, our calcium, our potassium, and more sodium stuff is going to get in there too. So we're getting into the complex silicate structures. So we're getting sheets and we're getting framework silicates. So we're getting that three-dimensional silicate structures. So like roughly 65 to 75% silicate by weight. So we're going to get a lot lighter. Because we're lighter, we're going to have a lot more silicates. Because we have more silicates, that means we have more resistance to flow. So this is going to be more viscous stuff. Keep that in mind. And what are felsic rocks? Good examples of it. Granite is the most common one. It's intrusive. Granite is made up of quartz, hornblende, pyroxene, and feldspar. So quartz and feldspar are the biggest portions of it. Both are very high in silicates. So that's why granite is so common on the crustal formations of the earth, continental crust in the earth. Rhyolite is very similar to granite. It's just a lot of ash and pyroclastic flows coming out of felsic volcanoes. Very light, very low density. All right, so mafic rock crystallizes from blank, temperature melt, and felsic rock crystallizes from blank, temperature melt. So go ahead and read through that process, see what you think. You guys on Zoom, go ahead and type your answers into the chat. Guys on Zoom seem to have it right. What do you guys think? Is it A? Is it B? C? D? E? Confusion generally? All right, so let's see, mafic rocks. Remember, we have that third line, that lighter green one. Are we at the highest temperatures? No, but we're still pretty high, so we'll go with high temperatures. Felsic rocks, we're at the bottom. Are we at high or low temperatures? Low temperatures. So the only one that makes sense is D. High temperatures and low temperatures. High temperatures for mafic, low temperatures for felsic. So that's going to be really important. So keep that in mind. High temperature mafic rocks, low temperature felsic rocks. So basically in general, mafic rocks start to crystallize from hotter melts. So the hottest volcanoes in the world are going to be sourced with mafic rocks. Felsic rocks crystallize with cooler melts, which makes sense because felsic rocks create more viscous lava. So the more viscosity we have, the more we can build up into higher and higher volcanoes. All right, so let's talk about the viscosity of these things. I know this is a lot of chemistry. I know this is a lot to wrap your brain around at 11 o'clock in the morning, but this will all make sense once we start to break them down into different volcanoes. So if we have basaltic magma, we're having mafic magma. So remember, basalt is formed at mid-ocean ridges. It's found in Hawaii. It's found in hot spots. So we're getting the highest temperatures, 1200 degrees C. It makes sense for the highest temperatures to be located at hot spots. Those areas are just magma chambers that are hot enough to melt through the Earth's crust. So we're getting the highest temperatures. Because we have the highest temperatures, we're going to have the lowest silicate content. And remember, silicate content is what's going to define our viscosity. So you decrease the silicate content, you're going to decrease the viscosity. So keep that relationship in mind too. Lower silicate content, lower viscosity. So that's why you get these runny lava flows that you get in Hawaii. This video is from Hawaii. It's from Kilauea. Kilauea is not a mountain. Kilauea is what's known as a shield volcano. It's a really wide, very, very large in area, but it's not very high in elevation. So because these are very runny and because they're more preferential to flow, they're going to spread out over a large area. So whenever you think of mafic magma and basaltic magma, think of Hawaii. We're not going to build up into a mountain, but we are going to spread out over a large area because we have such low viscosities. We're able to run everywhere, basically, with mafic magma. So andesitic magma, we're going to up our silicate content. We're going to decrease our temperature. So we get something that's kind of runny, kind of viscous, but it's still a lot lighter. So we're going to be able to build it up a little bit more. So if we look at Mount St. Helens, man, this is a terrible one. It's hard to see, but once this recording is up, take a look at that in particular. That'll really help. What you'll notice is this is from Mount St. Helens after it erupted. So before it erupted, Mount St. Helens was that picturesque, what you imagine as a volcano, large steep sides, crater in the middle. After it erupted, it was like this, one side of the mountain was missing. So now as you're watching the crater itself, it's going to start building up and up and up. So because it's more viscous, because we have more silicate content, we're going to get less flowing outwardly. We're going to get more buildup. So because it can't flow everywhere, it's going to start to crystallize quickly right at the source, and that's just going to keep building up and up and up and higher. So that's why once you get to felsic magmas, where you get more silicate content, you're going to get lighter, so you can go get built up higher, and we're also going to increase our viscosity. So that's also going to contribute to building up higher. So that's why the highest volcanoes in the world, ones with the steep slopes, are going to be made with silicate magma, felsic magma, high silicate content. Tell you what, let's take a 5-minute break, quick stretch, and we'll meet back at 11:11. Alrighty, so we've got three different magnetite mafic, intermediate or andesitic, and felsic. Each of these has varying degrees of temperature, varying degrees of silicate content, and that defines its viscosity and its preference to flow. So as we talked about before, Kilauea right here in the red box, out of the three of those, it has the highest temperature, 1170 degrees Celsius, compared to 1130 and 820 degrees Celsius. So remember, higher temperatures means lower viscosity. Higher temperatures also means lower silicate content. So is it going to be basaltic, andesitic, or rhyolitic at Kilauea? Who can tell me? Yeah, 33% chance. A, basaltic. Very good. That's exactly right. Basaltic magma, mafic magma, you're going to have the lowest silicate content, highest temperatures in order to form it. Forms at the hottest places in the world. So because Hawaii is a hot spot, it makes perfect sense. So let's say, let's take it to Momotombo. It's at a convergent plate boundary. We have the lowest temperature on this out of these three. Is it going to be A, B, or C? C. Why is that? Because it's the lowest temperature. So what does that mean? Highest silicate content. Very good. So once we get the lower temperatures, remember Bowen's reaction series, lower temperatures, the felsics were at the bottom. Quartz, muscovite, that's where all the silicate minerals are. So we're going to get higher silicate content. We're going to build up higher mountains, and we're going to have lower temperatures and lower viscosity. Excuse me, higher viscosity. So less preference to flow. Very good. Okay, so that's the magma. That's the rock and mineral portion. So now we're going to talk about the volatiles that are in the magma. So the liquid is the melt. The solid part of this portion is the minerals that compose the melt. And then, of course, with everything, there are gases in it. So as you're melting rocks, rocks aren't just regular solids. Every rock has pore space. And those pores can take in fluids and gases over time. It takes a lot longer than it would, say, just a regular sponge, but they'll still take in those volatile gases and fluids. So as you're melting those rocks, you're going to agitate those gases within the rocks themselves, and that's going to dissolve and impact the magma as a whole. So the most common ones that we get are, yes? Yeah, sure. No problem. You good? Yeah, no problem. Okay, so once we start dissolving it, what kind of volatiles are we going to get? So surprisingly, water is considered a volatile. Excuse me, man. So many multiple syllable words today. Water is considered a volatile, surprisingly. Even though water is one of the most abundant things on the planet's surface, water is going to soak into those pore spaces of rocks. It takes a lot of time, but you can still do it. If I put a rock in a glass of water and I let it sit there for probably 3 days, it will change its weight drastically. And it'll soak all the way into the core. Water will find pathways anywhere. It can go anywhere it wants. A lot of carbon dioxide gets trapped as well. You get a lot of bubbles in water that trap that CO2 from atmosphere, as well as sulfur dioxide too. You get a lot of those. That's more coming up from the deeper portions of the earth. So these are the most common ones that we get in these rocks. So as you get under pressure and deeper into the Earth's core, you're going to start to dissolve these. Near Earth's surface, you're going to exsolve them, meaning release of gases rather than breaking them down into the melt, which is dissolving. So volatiles, ultimately, they're going to change the rock by making it easier to melt. So they're not melting the rock themselves. They're just impacting temperature, pressure, destabilizing, and creating more energy to change the way the rock melts. So if we look at this phase diagram, this geotherm, which is just a curve describing the temperature, and how temperature changes with depth. So our y-axis is our depth in kilometers. Our x-axis is our temperature in degrees Celsius. That straight solid curve that we have, that's our geotherm. So as you can see, it's pretty steep for most of the Earth's crust. We're increasing in temperature rapidly with depth. But then once we get to this certain point, it starts to bend out. So that's where we start to get all of these volatiles, helping to make it melt the rock a lot faster. So up until that point, volatiles aren't playing a role. Once we get to that point, volatiles are going to start dissolving and exsolving, and that's where we get that faster and faster breakdown of rock. So as you can see, even if we were increasing in temperature this way, the temperature required to melt certain rocks is going to be lower because of the volatile content. The more volatiles you have, you don't need as much temperature to melt that rock down. So the dashed lines are melting curves for basalt. So you have wet basalt to the left, dry basalt to the right. Obviously, if you have wet basalt, we're talking about oceanic crust. Stuff that makes up oceanic crust is all basalt. So as those plates subduct, you're going to get decreases in temperature based on the water content, the lower you get in the crust. Once you hit that volatile infusion point, you're going to start increasing in your temperature. All those volatiles are going to start to dissolve, break down the basalt itself, and then that's where we're going to get an increase in our volatility. As you can see, dry basalt, that's a pretty standard curve because dry basalt doesn't have that water in it. It doesn't have that water vapor that's going to dissolve. It doesn't have the CO2 content. So that's why we don't see that drastic curve that we see with wet basalt to the left. So this is the same three volcanoes we were looking at a few slides ago. This is the volatile content to the left. And as you can see, the most common types are H2O, water, carbon dioxide, and sulfur dioxide. H2O for our conversion plate boundary, that's going to be almost 97% of the volatile content. In our hotspots, it's going to have a much lower volatile content. Remember, the magma source for hotspots is literally the center of the Earth. There's not a lot of, once you get to the center of the Earth, you're not getting a lot of water vapor at all. So there's a little bit there, but the source of that magma is not coming from any volatile content, really. But you do get a lot of CO2 because CO2 can sink down into different rocks, solidify, and then enter back into the tectonic cycle. So they do have an increased amount of CO2 in hotspot volcanoes. So out of the 3 V's of volcanic eruptions, we're going to start with volume. We're getting into actually erupting the volcano. So the amount of the capacity that the magma chamber can hold is going to be really indicative of how intense or powerful the eruption is going to be. As you can imagine, the greater the capacity of volume of magma, you're going to have a more powerful and more intense eruption. If you have more stuff there to erupt, you're going to erupt longer for a longer period of time at greater intensity. So for the example, Long Valley in California, this is a huge, huge magma chamber. So it's kind of similar to the eruption that we had a few days ago, where we have these two peaks at either end of the actual magma chamber. So the magma chamber is gradually feeding these two peaks over time. Eventually, there's a collapse, and there's just this huge explosion from the center of it. So that's what we had at Hunga Tonga a few days ago. We had these two peaks and the greater caldera in the center. And that's where the eruption was. That's where the magma chamber is. That's where all that material is sourced from. Now we get to volatiles. So think of a champagne glass, a champagne bottle rather. What gets the cork out is all the gases in behind it. As you agitate those gases, they want to push outwardly on all directions. So that's why that cork flies out of the bottle, because of all the forces in the gas coming out of it. So we have a low volatile. If we have a low volatile concentration, we're just going to get those runny materials, those runny lavas like we get at Hawaii. Not explosive at all. High volatiles, we're going to up the energy, we're going to up the melt. That's where we get our explosivity. No volatiles at all, you're not going to get an explosion at all. So volatiles are going to constantly be released as they're being dissolved. They're trying to get out. They want to rise. So if you have, as you can imagine, a more viscous magma, if you have something that's harder to it's harder to flow, it's going to be harder for gases to get out of it. Think about blowing bubbles with a straw in a glass of chocolate milk versus if you stuck a straw in a glass of honey and tried to do the same thing. It's going to be a lot harder. It's going to take a lot more force to blow bubbles in a glass of honey, right? So same thing here with magma. If we have more viscous magma, it's going to trap all that gas and that pressure is going to build up. So that's why more viscous magma creates more explosive eruptions. So now we're finally tying everything together into the eruption process. So if we have basaltic magma, remember basaltic magma, low silicon content. So what does that mean? We have higher density, we have lower viscosity, so we want to flow. We have more preference to flow in basaltic magma. And because of that, we have also low dissolved volatiles. So we don't have much of an eruption at all. So, man, I really got to work on making these more visual because I can't even read that and I'm all the way up front. But from the top down, we have Iceland and Hawaii. So Hawaii, we've got low water content, low viscosity, basaltic magma. We have low volatiles. So you don't hear about huge eruptions at Hawaii, right? You hear about these gradual flows that maybe flow into the street, maybe block off a road for a while that they have to reroute traffic, but nothing that's going to destroy the entire island. Just something that may cause a forest fire that you have to manage, but not a huge devastating eruption. Now, once we increase our silicon content, with increased silicon content, we're going to increase our viscosities. We've got higher viscosities, less preference to flow. We've got higher volatiles now too. So now we're going to build up and build up pressure until we get something like in Plania, very, very violent eruptions. Vesuvius is a really good example of that. This is where we get just that build up and build up until it just explodes, sends material everywhere, sends huge ash columns. So the combination of the viscous magma allowing the build up and build up of pressure with those volatiles is going to create a more violent eruption. right, now we talked about this. Talked about viscosity. And that's really the big takeaway. We have mafic magmas up top here. We have felsic magmas down here at the bottom. Mafic magmas, low silica, low viscosity. If you have low viscosity, you're not going to get a buildup of volatiles. And if you don't have a buildup of volatiles, you're not going to get anything eruptive, right? So this is the flow chart that we're going to use, starting with the chemical composition and ending with what kind of eruptive style we're getting. So mafic, low silica, low viscosity, less volatiles, less trapped volatiles, no eruption really. You get the removal of material, but it's not going to be violent. Now we get to our felsic, up that silica content. High silica means high viscosity. Viscosity means you're trapping those bubbles in the volatiles, and those trapped volatiles increase in pressure, and you get explosive magnets. So this is the takeaway from that entire 40-minute lecture that I just went on all of those. So make sure you get this down pat, because this will be important. And that's basically what it looks like in graphical form for those of you that are visual learners. So this is what we're working with. So we have our shield volcanoes at the bottom. This is Hawaii. Shield volcanoes are just large in area, not large in height. And as we're going up, we're increasing our explosivity, our volatile content, our viscosity, and our silica content. So as we increase all of those, we're going to get more explosive and more devastating volcanoes. All righty, I think that's a good place to stop. Tomorrow, we're going to talk about plate tectonics and its role in volcanoes and why certain plate boundaries have certain different types of volcanoes. And then we'll also discuss the different types of volcanoes and how their eruptive styles and chemical composition goes into it. All right, keep an eye on Canvas, get all your assignments done. And once again, if you haven't done exam 1, email me and schedule it so we can get those grades in, okay? Have a great Tuesday, everyone.
All right, Professor.
Yeah, Keaton.
I just had a quick question. Did you end up seeing that email that I forwarded along to you? I know I sent it. I accidentally sent it to M Powers at UDL
Yeah.
the first time. It turns out there's another Mike Powers at UD.
There is. He's gotten quite a few of my emails.
Yeah, I'm sorry to throw that at the guy as well, but yeah, I mean, I'm not sure what can be done at this point since I did take the test already. You know, I don't really expect any sort of redo. I just, you know, figured it just reach out and ask since I did try to, you know, ask ahead of time. It just circumstantially